right, welcome back, students. Here we're going to finish off our discussion. We're on topic 8.10. This is the buffer capacity. Now, we have talked about buffers previously. In fact, if I move back a little bit to 8.9, we were talking about the Henderson-Hasselbalch equation, how we were able to kind of determine the pH for a weak acid. And during that example, I made reference to this region here. Whenever you've got the base that's being generated at the same concentration as the weak acid, this ratio of base to acid actually becomes 0. And that leaves an equation here, an equality, where the pH is going to be equal to the pKa. So we know that buffers are going to be able to resist change. But like all things, that ability to resist the change is not going to last forever. And so we need to be able to figure out how long is it going to last, until what point. Is there a point in the titration where this is going to come to fruition, or where it's going to peak out? And so that topic is the topic of 8.10, which is the buffer capacity. So let's kind of look at the information that we've got available for us here. Now, the information here is not going to be very long. In fact, this is the only information you got here that I've shared or will share in the notes. But this is what we've got. The buffer capacity is going to be that amount or that position in a titration where that strong acid and the strong base, for example, if we're looking at those particular entities being mixed, that's going to be right at the point where the neutralization occurs. And that's pretty straightforward. That'll essentially be at equivalence point, because they're both strong acids and bases. They dissociate quite a bit, and they're going to be able to reach a point where the pH of the solution is a pH of 7. So we know that already. But that's not entirely the case with a weak acid or a weak base. So here, what we got to remember, though, is that when we look at the pH in this scenario where you have a weak acid or a weak base, that pH is going to be relative straightforward and balanced until there's no longer an ability for the weak acid. If we take that perspective, looking at a weak acid scenario, the weak acid isn't going to be able to neutralize any incoming base. And so the buffer capacity is literally just the ability of the acid to neutralize. And once it loses that ability to neutralize, it's not going to be able to do so anymore. Now, let me go to move the notes over here just slightly to the left to give us a little bit of space over here on the right-hand side. What I'm trying to do is kind of give us a little bit of a writing table. And I'm going to zoom in over here. And so why do I need this? Because what I'm trying to do here for us is I'm trying to bring us back to that titration graph. So at the beginning of the titration, remember that we had the curve. I'm going to go ahead and use here the red curve that I had before. We start off with a titration like this. It goes up, it curves, and then you wind up going that way. Now, if this were a strong acid, strong base, the titration curve would be a little bit more steep. In this region here, we would see a line come straight up and down that way. The one represented here, since we know it starts at the bottom of the pH curve, so over here on the y-axis, that y-axis is literally going to be pH, and so this is pH over here. Let me go ahead and write it. pH there. Remember, time is increasing to the right. So what's going to happen, since we are over here at the bottom, that means that we're starting in acidic conditions, and it's going to get up to pH above 7 conditions, so where it's going to be basic. So the main thing that's going to occur here is that if you're going to be looking at how well a buffer is able to work, how well is a weak acid able to neutralize the incoming base, it's going to be in this region right here. And so previously what I had done is I had shown you that this region here was the buffer zone, is what I had mentioned it as. This is the buffer zone. And the buffer zone is literally that region of the titration where the weak acid is able to do a really good job at neutralizing. And it's able to do that. It's going to be able to do so until it reaches a maximal point. That was the buffer capacity that we identified before. And that buffer capacity was going to be reached here. We assume that this is the equilibrium here. We kind of do a thing here. Half of that position is there, and then half of this position is about here, which puts us right about there. I'll use again the yellow arrow to denote where this is, and this point that I'm referring to here, this is the half equivalence point. This point here is where you're going to get max buffer. In other words, by max, I don't mean to imply that you're going to get, it's going to continue. This is the max limit of that buffer. So beyond that point, it's not going to be able to go forward and provide the same kind of neutralization that it provided for us previously. And so in this case, any additional stressor to the system that's going to be added, notably if you're doing the titration, it's going to be the hydroxide. So once you add more hydroxide, you're going to see that the pH is going to climb. And it's going to climb not in a very small incremental way that it did before, but beyond this point, the pH is going to rise quite dramatically in comparison. So this point, the half equivalence point, this is the point that I previously mentioned was the point where the pH is going to be equal to the pKa. This point here tells us the level at which you're going to have, perhaps if you're trying to figure out what's a dominant species inside the solution, is it going to be protonated or deprotonated? Think of it this way. If the pH is below here, so if pH is below pKa, what you get here is going to be the protonated. So you're going to get the HA version. But if the pH is greater than the pKa, you're going to get the A- version of the acid. In other words, there's going to be more conjugate in solution beyond this point. Now, any additional hydroxide that you add obviously is going to increase the pH here, so you're going to see pH rise dramatically. That's the main thing that this section on the buffer capacity is addressing. And so it's one that you really need to be able to understand. And the quickest way to understand it is find the half equivalence point, and it is from that point that literally clearly establishes the mark of where the buffer no longer works, because you've exceeded the capacity for the buffer to neutralize. Now, the last thing that I'll mention here before we go in this section and move on to the next one is going to be, well, what happens, why is it then, previously we had mentioned that one of the instances we wanted for a buffer or a weak acid was that you want it to be in excess. Well, the thing is, we definitely want it to be in excess, and again, just to reiterate that point, which I'm identifying here in the notes, is that we want the amount of the protonated version, the weak acid, to be in abundant supply, because it's that weak acid or the base here, the conjugate, it's going to be able to withstand changes to the pH. If you're adding hydroxide, the HA will be able to bind, the proton on the HA will bind with the hydroxide to form water, and on the other side of things here, the A- represents the conjugate. It'll bind with any protons that you add from an acid to reform the HA. So the idea overall, though, is that the higher the concentration of the buffer, that weak acid, weak base, it is, then that means that the better it's going to be able to neutralize. And the more that you have of it, it actually increases the capacity or the ability of that weak acid to neutralize. So the buffering capacity increases with concentration. They're directly related. So you increase the concentration of the weak acid, it'll neutralize more. The capacity to do so increases. So if you keep reading, the little idea here is being able to critically identify the point where the half equivalence point is going to be. That's the area that's going to be able to give you the maximum capacity for buffering. But anything beyond that, the weak acid won't be able to resist any more changes to pH, and we will see the pH rise dramatically. So that is the buffer capacity. And so with that, I'm going to go ahead and move on to the next topic, the final topic in the unit, and that will be Unit 8.11. So in Unit 8.11, this is dealing with pH and solubility. The pH and solubility is a pretty straightforward concept using all the things we've looked at before. So we're going to tap in some information with respect to the common ion effect, its effect on dissociation, and we're going to look at the ability of a compound to essentially dissolve. And we're going to look at some factors that kind of lead to that particular compound dissolving. And so you do need to engage in a little bit of review. So make sure you go back and you look at some of the solubility rules that we had shared before. And so I'm going to go and put that main screen here. Spend a little bit of time reviewing these, and again, remember that solubility is typically going to be represented by a number. The higher the number for K, the greater the solubility. It means that if you see a compound with a high K value, the higher the value above 1, then more product is going to be produced, and that is always favorable. So solubility is affected by many factors. You can go back and look at all those factors. The most notable of factors was temperature. You increase temperature, solubility increases. And the opposite is true. If you reduce the temperature, make things cool, or cool things down, the solubility goes down. We also saw in Unit 7 the idea that there were some stressors, like if there was a common ion. And so if you look at the notes that I'm referring to here, let me move this up a bit. I'm referring to this section of the notes, the common ion. And in that particular section of the common ion, remember there, if you add a common ion, if you have a dissociation where one of the compounds is leading to an ion and you have another compound reaction, dissociation, that's leading to the formation of an ion that is common to the first, we have a common ion scenario. And typically what that does is that it creates a condition where the concentration, you've reached solubility maximum, so you've saturated the solution. From a K and Q perspective, you establish a situation where Q now is a lot greater than K because the concentration of the common ion is leading the products to be greatly higher than the reactants. And so this is going to cause a shift to the left in that particular reaction. So the solubility, from a solubility perspective, the KSP value will go down. And so the main thing that we need for you to know in this section is, well, what happens to a compound solubility? Does it go up or down? Since we've been talking about pH all this time, the question becomes, what happens? And so I've already got a question for you. The question becomes, what happens to the solubility of a compound? Let's say this one here, MgOH, magnesium hydroxide. What happens to the solubility of this compound under different conditions? What if we raise the pH or whether we lower the pH? So the question I'm posing to you before I go any further is, I'm going to put this question here in the front. I'm going to ask you, normally we would have done this in a paired discussion in class, but for right now, just on your own, consider what would happen to the solubility under normal conditions. You're not adding a common ion or anything like that. What happens to the solubility of magnesium hydroxide? First off, and then we're going to consider two alternating conditions. We're going to lower the pH in the first instance, and then we're going to increase the pH in the second. But for right now, just normal solubility. What is the solubility of magnesium hydroxide? What's it going to look like? Well, if you're looking at the notes here, the simple answer is that magnesium hydroxide, if you go look up the K values for it, it's not very soluble. In fact, the KSP value, if you look at the notes here, are indicating that that value, the solubility product value, is 5.61 to the negative 12. This is a very small, very low solubility rating. So it might dissociate, and you can see it here, but it's not going to be very much. The molar solubility of this particular compound is going to be pretty darn low. But you can go ahead and calculate it. You can definitely do a K expression or a K Rice table and figure out the K value, or rather figure out the X value using that K expression value, and you can figure it out. I won't necessarily do that here. What I want you to be able to do is I want you to be able to consider the alternating facts. So under normal conditions, if this is the solubility value, very small, what happens under two conditions? I think the first condition that I mentioned was, what happens if you increase the pH? So let's kind of consider this one here. What's going to happen if you increase the pH? Well, if we kind of underline a couple of things just to bring our attention to it. What's going to happen when we increase pH? Well, since pH is determined by the concentration of the proton, that means if you increase the pH, then pH concentration clearly has to go down, because if pH is going up, that's putting us into the basic realm. When you increase the pH, the concentration of the hydrogen ion is going to be significantly smaller than the hydroxide concentration. So literally the concentration of the proton is going to go down. So if you look at the notes here, this scenario is discussed, and what we're saying to you here is the following. What I'm trying to share here with you is that if you take that NaOH, magnesium hydroxide, that magnesium hydroxide already with this small value of 5.61 to the negative 12, the pH goes up, and in this scenario, that means that you're going to have a lot more hydroxide in solution. Since the hydroxide in solution is going to present a scenario now where it's common to the dissociation, so you notice up here in this section here, let's go ahead and circle it. In the reaction, you're going to generate hydroxide. And if you increase the pH of the solution, because you're introducing more hydroxide yourself, maybe you're adding hydroxide from another solute that is able to dissolve, but doesn't matter how you add it. What is going on here is that you're getting an influx of OH. So you have a secondary reaction, let's say reaction number 2, it's going to generate hydroxide ion. So now what we've got is we've got hydroxide being generated by the first reaction. We got hydroxide generated by the second reaction. This is the scenario of a common ion. Now we don't need to go through all the details of what is going to occur in terms of concentration. We know that the concentration of the hydroxide is going to increase on the right side. So what you can think of here is that we are literally adding a stress. This stress is being added right here. And the stressor is the addition of hydroxide. That is going to cause the reaction to shift to the left. So that means that the solubility of the magnesium hydroxide, which was already low to begin with, is going to get even lower. So less of it is going to dissolve. Okay? And so that's what's going on here. Now, what happens in the other case? What if we were to lower the pH? Well, let's kind of look at the question. So what happens to the solubility of magnesium hydroxide when you lower the pH? Well, lowering the pH means that the hydrogen ion concentration, which is the main factor that affects that in the affirmative, that means that the concentration of the hydrogen ion is going to increase. And so increasing the hydrogen ion concentration actually produces a situation. If we bring that reaction back, let's just show you the info here. I'll zoom out enough so you can see the cases here so I can refer to the numbers. So the reaction is still the same. You can see the reaction up here at the very top. The magnesium hydroxide will dissociate very small amount, but it is going to generate magnesium ion, and it's going to generate 2 moles of hydroxide. So those are in solution. And so when the pH goes up, and so let's make this very clear here. So this particular scenario here, is when the pH goes down, and this scenario over here is when the pH goes up. Under the pH going down scenario, what's going to happen is that the hydrogen ion concentration is going to go up. It goes up because what's going on here is that in order for the pH value to go down, because it is an inverse relationship here, the concentration has to be higher in order for that pH value to come down. And when it does, that means if there is more hydrogen ion in solution, this hydrogen ion, let me go ahead and circle this in red for us. So this hydrogen ion here is then going to be able to combine with any hydroxide that's already in solution. So let's go ahead and be purposeful about this, write it out. And so let me kind of move this up a bit, and then I will write the 2 reactions down below, and then we'll go from there. All right, so here we are. So here we've got the dissociation of the magnesium hydroxide. We already know it's a low value, but notice here we already have hydroxide in solution. So when you reduce the pH of the solution, because you're adding maybe acid or whatnot to it, that means that you're going to have more hydrogen ions in solution to react. And the end result of that is when these 2 things are in solution, the hydrogen immediately reacts with the hydroxide. That'll generate the H plus the OH minus to form H2O. We know that this is a K value here, not a KW, but a K value that is going to be equal to 1 times 10 to the 14. It is extremely favorable. And so if you think about what's happening here is as the pH drops, because you manufactured that situation, you created the pH conditions being lower, a lot of the hydroxide is going to be taken and reacted. It's no longer. So what is going on here, if you think about it from the Le Chatelier's perspective, what you are essentially creating by doing that is you're creating a stress here. but the stress is removal, so it is a taking away of the hydroxide because it's no longer in solution. So that is going to drive the reaction to the right to produce more of the hydroxide, which leads to an increased solubility of the magnesium hydroxide. So in the grand scheme of things, because if I scroll up here, the solubility value up at the very top, if you see that number up here, the solubility value was very low. But if you lower the pH, then that means that we're going to generate more hydroxide, so more of this magnesium hydroxide will dissolve to produce the hydroxide because it's being consumed by the increased proton concentration in solution that we created when we lowered the pH. And so the end result here is that the reaction makes the magnesium hydroxide, or the salt, more soluble. So the inverse relationship here is if you increase pH, it creates a decreased solubility. And if you decrease the pH, you increase the solubility of a salt in solution. So those are the remaining topics that I needed to cover here. That's topic 8.11. Continue to review the notes, continue to watch any video lessons that you may need to prepare for the exams, and we'll see you next week.